Welcome to the final video of the FP3 chapter, Integration. In this video, I'm just going to show you the application of the formula for the surface area of a shape of revolution. If you would like to see the derivation of that, it's quite long, so I put it on as a separate video. You won't need to know that for the exam, but if you're interested, check that out. However, before we go on, there is one thing to be clear on, and that is what this actually means, because you might not have seen this before. So a little picture here to help you understand what's going on in this video. The surface area of revolution means the surface area of the shape formed, the solid shape formed, if you were to rotate the arc of a curve around the x-axis 360 degrees. So in this picture here, you can see the red arc, y is equal to a function of x. And if you were to take that arc and rotate it 3 dimensions out of the page, around into the page, and back to the front, it would describe a solid shape. In this case, something that if you were to turn it on its side, it looks a little bit like a vase. In P4, you would find the volume of that shape. But in FP3 here, we need to find the surface area, which is why you can see in this picture, it's a hollow shape, and you can just see the strip of the area around the middle here. So this is what we mean. We mean finding the surface area of the shape that would be formed if you rotated the arc of a curve around the x-axis 360 degrees. Or, of course, around the y-axis if you went that way. So here are the formulas. It can be shown, that is in the derivation video, that the shape generated by rotating an arc about the x-axis has the surface area according to this formula. And you'll notice it's very similar to the length of an arc because that is part of the formula of how you get the surface area. So we've got 2 pi times the integral from x1 to x2 of y times the square root of 1 plus dy by dx squared, integrated with respect to x because it's about the x-axis. Main difference, or the only difference here with the length of an arc, is that we use capital S for surface area instead of small s for arc length. There's a 2 pi in front, and you're timesing your square root by the function itself before you integrate. Same in the parametric form, this is the difference here. And if you were to rotate this about the y-axis, then you could get a whole different formula, but it's more common to use this formula that I've got here, which I've made a little mistake on. It should be x1, x2. Because what you can do is use y1, y2, dy, x here, dx by dy squared here, but it's not very common to have x as a function of y and to integrate with respect to y. So what we normally do is rearrange that using the definition of the arc length, and you can get this formula instead, which is using x1, x2, integrating with respect to x, and the square root is the same as the other one, but the key difference is that instead of a y here, instead of the entire function, you just multiply by an x by itself. And that will be around the y-axis. It's important to remember this, because although this one is in the formula booklet, this one is not. So if your question happens to be rotate about the y-axis, you need to remember to change that y into an x. Same with the parametric form. Everything's the same except this y changes into this x. So here are the formulas, and this video, the bulk of this video, will be going through some examples because they're quite long. These examples are in the textbook, but the textbook does not lay out every single part of the process, and a couple of the parts they skip a little bit more than I would, so I'm going to be meticulous in writing out every part of the process so you can see exactly where it's coming from, which does also mean they are quite long. This video is quite long, so brace yourselves. So here's our first example. The curve C has equation this. The arc of the curve between the points with x coordinates 1 and 3 is completely rotated about the x-axis. This is nice and formal. This is telling you it's a full rotation, so it's a full 3D shape rather than just half of the shape. Find the area of the surface generated. So we're going to use this formula here with y is equal to this from x equals 1 to x equals 3. Similar to the arc length, I'm going to do a lot of the algebra work with this section before I actually put it into the integral. So we'll get all of that out the way, we'll simplify it all, and then we'll try and integrate it afterwards. So here we go. First of all, I'm going to write y in terms of indices, and I'm going to expand out that bracket. So it's a little bit easier to see what's going on. Y is equal to 1/3 x to the half times 3 minus x. So that is equal to x to the half minus 1/3 x to the 3 over 2. So when I differentiate that, I get a half x to the minus a half minus 1 over 2 x to the 1 over 2. So that's the derivative. Now for the rest of the square root, I need to square that and add 1. So let's do 1 plus the square of that. 1 plus, and then this thing here squared gives us 1 over 4 x to the minus 1 minus 2 of these, so that's 1 over 2. And x to the minus half times x to the half is gone, plus 1 over 4 x. Now here is a sneaky trick that we saw on the previous video, that going from this step to this step, because we've added a 1 here, the only thing that changes is that this minus a half becomes a plus a half when you put these two together. So what we end up getting is something very, very similar to this thing squared, but where the minus has changed into a plus. So let me write that out. We get 1 over 4 x minus 1 plus a half plus 1 over 4 x, which only because of the work we've done getting from here to here, I can recognize that this becomes 1 over 2 x minus 1 over 2 plus 1 over 2 x to the 1 over 2 squared. And again, I would only really see that because of the work that we've done going from here to here. That wouldn't be in my head straight away to do that. But it is a sneaky little trick that comes up a few times. And that simplifies nicely because putting that into a square root allows the square root and the squared to cancel, and we just get the terms in the bracket multiplied by the y function, which I'll use this for. So putting it all into index form, y times the square root of 1 plus dy by dx squared is equal to y, which is this, times 1 over the square root, 1 plus dy by dx squared square rooted is the bracket on the bottom left. And as mentioned, the square root and the square cancel out, so I don't have the squared here anymore. Multiply all of this out, and we get 1 over 2 minus 1 over 6 x, and plus 1 over 2x, and minus 1 over 6 x squared. And that is equal to 1 over 2 plus 1 over 3x minus 1 over 6 x squared, which is a surprisingly nice integral. Integrand, I should say. Because when we put that in here, it's just 3 separate terms. I can integrate that very easily. So capital S is equal to 2 pi, the integral from 1 to 3 from our question, 1 over 2 plus 1 over 3x minus 1 over 6x squared dx. And I hope you can see that we have done most of the work in this algebra section here. And the rest is just following through the integration and putting in the numbers. Let's do that for completion's sake. X over 2 plus x squared over 6 minus x cubed over 18 from 1 to 3. With the 2 pi in front, can I fit it all on the screen? We've got 3 over 2 plus 9 over 6, which is another 3 over 2, minus 27 over 18, which is another 3 over 2. That's the first bracket, minus 1 over 2 plus 1 over 6 minus 1 over 18. Oh, almost, yes, just about. Okay, that's gone, so that's 2 pi times 3 over 2 minus 1 over 2 is 9 over 18 plus 3, oh, stick all this on your calculator, 9, 10, 11, 12, 11 over 18. I hope that's right. Turn this into an 18, multiplied by 9, so that's 27. And we've got 16 over 18. Cancel the 2, should give us 16 pi over 9 as our final answer. And that's the first one done. It didn't take quite as much space as I expected because I had another slide for the overflow. Here is the other slide. So moving straight into the second example. Here we go. The arc of a curve with equation y equals cosh x from the point 0, 1 to log 2, 5 over 4 is rotated completely about the y-axis. Let's put a big old circle around that. And straight away, we should change this into an x so we don't forget later. Find the surface area of the surface generated. Okay, so it's basically the same idea, but this time, instead of y times the square root of all this, we're going to have x times the square root of all this. So let's get straight into it. Same as before, I'm going to start off just considering that bit inside the square root. So if y is equal to cosh x, dy by dx is equal to sin x 1 plus dy by dx all squared is equal to 1 plus sin squared x, which I'm sure you remember from our identity work is cosh squared x. And that's quite nice because when we do the square root of cosh squared, we just get cosh. But we do have this x out in front as well. So x times the square root of all of that is equal to x times cosh x, which is the thing that we're going to have to integrate. Which isn't all that nice, but we can do this with integration by parts. So if I write out our formal question here, capital S is equal to 2 pi times the integral from 0 to log of 2, because remember, although we're going around the y-axis, if we're going to use this form of the formula, we're still using x1 and x2 here, so 0 to log 2 of x cosh x with respect to x. Now I'm going to do this nice and formal on the screen, so I'm going to label, I've got u, and I'm going to make that my x, and for the formula I also need dv by dx, which will be the other part of the product, cosh x. So du by dx, differentiate x as 1, and v integrate cosh is sin. So applying the integration by parts formula, which is in your formula booklet, we can write 2 pi times u times v, so that's x sin x, and that needs to be evaluated at 0 log 2, minus the integral from 0 log 2 of v du by dx, which is just sin x times 1. And all of that is multiplied by 2 pi. If I put 0 in here, I get 0. If I put log 2 in here, I don't get 0. So we'll come back to that in a second. For now, I'm going to finish off the integration. And the integral of sinh is cosh. Of course, that is also evaluated 0 to log 2, and the whole thing is multiplied by 2 pi. Now what I'm going to do, because I've got this log 2 as one of my limits, I think it's going to be easier, unless you happen to have a calculator, which I don't at the moment. You could put it straight in your calculator. But if you don't have a calculator, or you want to see why the calculator is giving you the answer it is, putting log 2 in here, we can use the exponential definitions of sinh and cosh. So I'm using quite a lot of space here. I've got 2 pi times log of 2 times sinh of x, and sinh is e to the x, so that's log of 2, minus e to the minus x, so that's minus log of 2, all divided by 2, minus the 0, because the 0 bracket is obviously 0. So we've got that bit there from the first square bracket inside, minus cosh of x, so we've got e to the log 2 plus e to the minus log 2 all over 2, and that minus cosh of 0 gives us e to the 0 plus e to the 0 over 2, which is a 1. Now I'm going to have to move on to my next slide here. So let me say that there is equal to a 1. And what we're going to do on each of these is we're going to take the little minus signs up here and make them a -1 index inside the logarithm. Maybe I'll stick this up here for now. 2 pi, big brackets, log of 2 times, so here my exponential log 2 becomes 2, minus exponential log 2 minus 1 becomes a half. So 2 minus a half over 2. And then minus down here, same idea, 2 plus a half over 2 minus 1. I think I'm going to need to move on to the next slide. I might have to move back and forwards to copy it correctly. So we've got 2 pi log 2. Let's quickly calculate this. 2 minus a half is 1.5. Divided by 2 is 3 over 4. And over here we've got 5 over 2. 5 over 4 minus 4 over 4 is 1 over 4. So we've got s is equal to 2 pi times log of 2 times 3 over 4 minus 1 over 4. If we put that 2 inside the brackets, we can see that that cancels. I get a 2 there, a 2 there. So we end up with 3 pi over 2 log 2 minus pi over 2. That's 2 pi over 2 and 3 log 2 minus 1. Either of those is probably our simplest form. And there we go. I hope I haven't made any obvious mistakes with my calculations. I should try to have a calculator handy at all times. Our final example is very similar, but we're going to use parametric equations. So if you're happy with it, you can stop the video, go ahead, practice the exercises, but if you'd like to watch the parametric example, then keep going with me. So here we've got the parametric formula, and scanning the question, it says the x-axis, so this y will stay as a y. So this is exactly the formula we're going to use. Parametric equations, x equals this, y equals this, from 0 to 2 pi, and it's a full rotation, 360, so we don't need to worry about scaling it in any way. Find the area of the surface generated. Alright, let's dive right in. As usual, I'm going to do the bit inside the square root first, and then stick it in the integral later. So if x is equal to t minus sine t, then dx by dt is equal to 1 minus cos t. For the y, we've got 1 minus cos t, and we differentiate that with respect to t, and we get, no we don't, sine t. Yes. Okay, and then we're going to square them both and add them together. So this one here squared plus this one here squared, and maybe you can already see why this is going to simplify. So we've got a 1 minus 2 cos t, and then we've got a plus cos squared t, and we've got a plus sine squared t. And of course, cos squared t plus sine squared t equals 1. So we've got 2 minus 2 cos t. Now, what we're going to do is square root this and multiply it by y, which is 1 minus cos t. And if you were to factorize this, 2 brackets 1 minus cos t. So we've got 1 minus cos t coming up quite a lot here. But we're going to have 1 minus cos t times the square root of 2 times 1 minus cos t. So it's getting a little bit messy, but let me put that in to show you where we are at the moment. Like this, and we're integrating from 0 to 2 pi. Okay, this looks pretty horrible. However, there is an element of sameness here. We've got 1 minus cos t, 2 minus 2 cos t. In order to integrate this, it's going to be a little bit messy unless we do one of our little tricks. And this is one of the good reasons for doing lots of questions, because the more questions you go through and struggle with, and the tricks that you find, the more you'll be able to use those tricks in other questions. So here, our trick is going to be not to leave it as 1 minus cos t, but to apply our double angle formula with a sine squared. So let me write out the one that I'm going to use. We've got 2 sine squared t would be equal to 1 minus cos 2t. Just trying to think if I've got that right. I always get my minuses and my pluses mixed up on these. I think that's right. Okay, but you might ask, how does that help us? Because we don't have a cos 2t, we've got a cos t. But that's okay, because what we can do is we can change this identity slightly. Excuse me, title. I'm going to do 2 sine 2 t by 2. And that will equal 2 times t by 2, which is t. So this is quite a sneaky little trick, and it's going to help us to combine the number here and the cos here, a number here and the cos here, into single sine parts that we can put together. Especially because we're going to have a squared and a square root, it's all going to be a little bit easier to see how we're going to integrate this. So if we stick all that in, I'll try and be careful with all the 2's floating around. So 1 minus cos t, I'm going to replace that with a 2 sine squared t by 2. And if you're thinking, oh, I would never have thought to do that, you're in good company. I would never have thought to do that, except that I've done it in questions before. So seeing this example is what will help you to see that you might have to do this in the future. Okay, timesing that by 2, so I've got to change this again. This is a 2, this is a 2, this will be a 4. So inside the square root, I'm going to have 4 sine squared t by 2 dt. Which is quite nice because the square root of 4 is 2, and I've got another 2 here and another 2 here, so I'm going to pull all of those out and make that 8 pi integral from 0 to 2 pi sine squared t by 2 times the square root of sine squared t by 2 is sine t by 2 dt, which gives me what is actually looking still quite horrible. S is equal to 8 pi integral from 0 to 2 pi of sine cubed t by 2 with respect to t. And yes, this will use one of our FP3 integration techniques, because we've seen so far in the chapter an example like this, where we said small odd powers of sine or cosine can be integrated by splitting it into an even power and a single, and then using the cos squared sine squared identity. So let me walk you through that. So we're going to have sine squared t by 2, which I'll apply the identity straight away, so we get 1 minus cos squared t by 2 in order to replace the sine squared, so 2 of these 3, and then there's still 1 sine t by 2 left. So I've split this into a sine squared and a sine. The sine has stayed there, and the sine squared I've changed into a 1 minus cos squared. Why do we do that? Oh dear. Because when we multiply that out, we get a sine t by 2, which we can integrate directly, and a minus cos squared t by 2 times sine t by 2, which we can also integrate directly, because this is a bracketed power, or a powered bracket, times by its own derivative. So this thing, if you remember your patterns, your standard patterns, this thing has come from a cos cubed, because when you differentiate cos cubed, you get 3 cos squared times by sine. And that's the pattern we're going to use to integrate this.
So integrating this, we have 8 pi times by the integral of sine t over 2, that's minus cosine t over 2. I'll put that in brackets because I also need to divide by the derivative of that t over 2. So dividing by 1 over 2 is multiplying by 2. Then minus, and we have this thing combining, as I said, to give us cos cubed t over 2. And again, we have to divide by the derivative of t over 2. So we're multiplying by 2, but we also have to divide by the new power, a 3. Now you might have noticed that the audio and the visual have changed slightly from the previous line, and that's because this is an edit to the original video where I made 2 mistakes. The first mistake I made here, forgetting to realize that when you do this, the minus has to change to a plus. You can convince yourself of that, I hope, if you think about differentiating this. The 3 comes down, it cancels with this, that's fine. That gives you cos squared t over 2. But then you also have to differentiate cos t over 2, which gives you sine t over 2, with the 2 coming out to cancel with this. and that's all fine, but the cosine, when you differentiate to give sine, it actually gives you minus sine, so this minus comes from there, and this should be a plus. That was my first mistake. Putting the numbers in was my second mistake. I made the ridiculous claim that cosine of pi is 0, when of course, as an eagle-eyed viewer corrected me, it is in fact minus 1. So here we go, let's try that again. S is equal to 8 pi, then we have minus cosine t, which is 2 pi divided by 2, so cosine of pi minus 1 times the 2 with the minus here gives me a 2. Same here, put 2 pi in, divided by 2 we get pi, cosine of pi minus 1 cubed is minus 1, so we have a minus 2 over 3. Our second limit is a 0, cosine of 0 is a 1, so we have minus 2 here, and then we have a plus 2 over 3 for the second one. And if you do that, we have 8 pi times 8 over 3, which gives us the final answer, 64 pi over 3. So that's the end of this third example, noting that the application of these formulas is what you need to focus on here, practice, 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 and little tricks like this one that we talked about here. And that should be enough now at the end of this chapter to practice from exercise 4H for these formulas, the chapter 4 review questions for all of the integration work, and we also now hit the review exercise 1 in the textbook, which covers everything from the first 4 chapters. And maybe I'll see you in the next chapter for vectors.